D.2, Introduction to Brute Force Method. In our last part of Module 2, let us learn this brute force method. We have learned this method a little bit before, but at this part, we like to, from the theoretical point of view, to study this simple method. First, description of the brute force method. First, let's look at the properties of brute force method. The first one, it is a straightforward approach. Okay, so you do not need to use any special way on the computing problem. When you get a computing problem, you just use the simplest, straightforward, almost everybody can get that, simple idea to solve it. Yeah. All right. You can always apply it to a problem. Yeah. Because, sometimes, because here we do not consider if the solution is good or not, right? We do not need to consider it. Yeah. Even you can try all the possible cases, right? Think about it. Yeah. You can try all the possible cases to solve that problem. It could be a very bad one, but your goal is just find a solution, whatever the cost is. Yeah. So from that point of view, so you can always apply it to a problem. Yeah. But in the real world situation, even this simplest way, straightforward way, sometimes you may not be able to do it. The reason is if you try all the possible cases, you may not have that kind of resource. So that is another issue. So the resource limitation issue. Yeah. All right. In general, it is not the best algorithm, especially when the problem is non-trivial. When the problem is non-trivial, okay? For the trivial problem, you can use the brute force method to get the best solution. But most of the cases, the problem is non-trivial, then you cannot expect the best solution or even near best. Impossible. The brute force method cannot give you that kind of solution. So that is our expectation. All right. It is usually used as the starting point for more advanced algorithms. So we know most of the time we cannot expect to get the best solution or near best solution, but this method has its value. So what is its value? We can use it as the starting point for more advanced algorithm. Yeah. Before we find an acceptable solution, let us find just the one solution first. Yeah. So let us just try the brute force method, find one solution first. When you do that, you get some experience. You understand the problem better. So with that kind of background, with that kind of knowledge, then the next round, you try to improve it. So that is another common approach that people use. So that's our starting point. But after we get a solution, brute force solution, we want to go to the next level, try to get a better solution. All right. The efficiency difference between the brute force method and the more advanced algorithms could be huge. Yeah, the improvement could be huge. So it's worth try for a better solution. Yeah. We have an example. In our module 1, we learned one example that gives us this kind of experience. So what's that example? Polynomial evaluation problem. Look at project 1, I assigned, so you're working now. We compare two different types of solution. The first type, method 1 and 2, both, that's the brute force method, right? Brute force method. Yeah. You evaluate polynomial in a straightforward way. The second, Horner's rule. That's our advanced algorithm. So you will see the difference is huge. Huge. Yeah. All right. Next, we will work on a problem. Yeah, the problem we solved it before, but this time we tried to solve in a different way. Yeah. All right. Problem number 4, sort and array. Yeah. Yeah. Here we revisit this problem again. Yeah. Yeah. Because this sorting algorithm, sort and array, this problem, for this class, we will do this many, many times. Yeah. All right. So you may ask this question, why we need to solve it another time? We already have a solution, but why we need to solve it another time? Yeah. First, our first solution is not an efficient one. It's not an efficient one. Yeah. Based on our analysis, it is bigger of n squared, right? Our first solution by selection sort, bigger of n squared. We can do better than that, right? Second, so here let me describe another important view of this, the reason we want to solve the same problem several times. Yeah. So our view, we take this. A problem is a carrier of a set of thinking methods that result in different solutions. Here, when you find a solution, you need to use a special thinking method, right? You need to use a special thinking method. Yeah. In this special thinking way, you find the solution. Then you can change a different thinking way, right? For the same problem, you can change a different thinking way, you get a different solution. All right? Then another different thinking way to get another solution. Right? So here we treat this particular computing problem. So let's say sorting problem. This particular computing problem, we treat it as a carrier of several thinking methods. So that will be variable. So one problem that can carry many useful thinking methods. How about that? How about that idea? We know thinking methods are valuable in the real world. Problem solving, right? Real world problem solving. We need to use various thinking methods, right? How do we memorize those thinking methods? We need some special carrier, right? Yeah. Special computing problem. So those computing problems we use to carry special thinking methods. So that is our view. Yeah. So the thinking methods are important to help us solve other problems. One particular thinking method, we can use it to solve many different other problems, right? Yeah. But the thinking method It is a not concrete object, right? It is not a concrete object. It is something in your mind. So you need some special way to carry it. Yeah. Here, our computing problem. Sorting computing problem. That is our carrier. Yeah. In this carrier, we put multiple different thinking methods inside it. How about that? Look at this view. Yeah. So this is an interesting view. Yeah. So that's the reason we want to explore many different, smart, advanced thinking methods for one particular computing problem. Yeah. So that is the view. Yeah. All right. A view based on a special property. Yeah. So now, how to look at this problem? View is important. Yeah. But how do you get that view, right? How do you get a special view? For one computing problem, you have so many different ways, different angles to look at that problem. But which angle, which view you want to take? That may not be easy, right? That may not be easy. Yeah. Here, I pointed out, so here, special property, you need to find some special property, and based on that property, you can have a special view. So get that special property, that is important. All right, so for this, here we use the problem number 4 as example. Yeah. So let us look at from our new understanding. Yeah. We want to get a new view. How to get a new view? We need to find a new property. Yeah. Now let us find that new property. Then we get a new view. By that new view, we have a new thinking method. How about that? Yeah. So that is what we are going to do now. Yeah. All right. We do observation. Yeah. So let us look at this problem closely, yeah, but different from our previous way. Remember, we have a previous way. So here we need to take a different way, different view on it. Yeah. All right. So the question, what is that property? We need to find that property. So usually this step is not easy. Find the property in a new problem. This step is not easy. Yeah. So you really need to do a good job to find it. Yeah. Here, let us use a simple diagram to find that property. Let us do some analysis work to find that property. Yeah. Suppose this is the array, given array. Yeah. We want to work on it. Yeah. All right. So when we work on it, think about our goal, make this array sorted. Yeah. All right. If this array is not sorted, so we want to check if this array is not sorted, what property does it have? Yeah. So let's look at it in that way. If this array is not sorted, what property does it have? Now, here I focus on a pair of two adjacent elements. Let us assume this whole array is not sorted, not ordered. Yeah. Can we say we can find two adjacent elements? Two adjacent elements, they are out of order. Can we say that? Can you see that fact, that property? Because if you can think in this way, the opposite way, if every two adjacent elements are in order, in ascending order, then we will get the whole array sorted, right? If every pair of two adjacent elements are in order, then the whole array must be in order, right? Yeah. That's a simple observation, simple fact or property. Yeah. But we assume this array is not ordered. If it is not ordered, then somewhere it breaks. Somewhere the property for the ordered array must break. Yeah. This is the place out of order. Yeah. You can find at least one location. There is one pair of adjacent elements out of order. How about that? So this is the new property we explore, we develop, we discover. All right? So this property, we want to use it to have a new view on this problem and find a new solution. All right, so next, observation for critical property. So this is a critical property. Yeah. All right. If the array is not sorted, there must be two adjacent elements that are out of order. How about that? Yeah. So that is our conclusion. Yeah. The property. Yeah. All right. Here I give you the reference in our textbook. Yeah. If you want to, get further reading material, you can go to section 4.1 for this part. Yeah. All right. So next, I want to introduce a new concept. It is called inversion. Inversion. Yeah. So what is an inversion? So a pair of elements, AI, AJ, is called an inversion if I less than j, the subscript I less than subscript j, but the element value a sub I is greater than a sub j. That is inversion. Inversion out of order. So this concept corresponds to our, description. Two elements. Here we do not assume adjacent elements. Here just arbitrary two elements in the array. We can define inversion concept. Now, a sub I, a sub j, anywhere in the array, we only need I less than j, but their values ai greater than aj. All right, so that's the concept, inversion. Yeah. Now we want to this new concept to characterize or describe the new property to give us new view on this problem. Yeah. All right. So if the array is not sorted, there must be an inversion, right? Yeah. So that is the first observation. Now, if the array is not sorted, there must be an inversion. If, in other words, or in the opposite view, if an array does not have any inversion, it must be sorted. It must be sorted. No inversion, it must be sorted. Right? So then, the opposite way, if it is not sorted, there must be at least one inversion. That's simple. All right. Now, then another improved view. Yeah. Improved view. Yeah. If the array is not sorted, there must be an adjacent inversion. Adjacent inversion. Because here we want to connect to our critical property, adjacent, two adjacent elements. So that related to adjacent inversion. Here we want to improve it. We want to improve from arbitrary inversion to adjacent inversion. Yeah. You will see this improvement will give us a better way to manipulate our data. Better way, yeah, easier way. Because we can change from a global view to a local view. So what is global view? What is local view? Yeah. So here, global view, yeah, the inversion, arbitrary two elements in the array. So it is a global inversion. That's the global view, right? Now we only look at the two adjacent elements. Local inversion. That's the local view. Yeah. You can see to work on the local inversions, it is much better than work on the global inversions. How about that? How about that? Yeah. So that would be, much easier, right? So working on the data locally, much easier than working on the data globally. Yeah. All right. Next, the question, how to fix it? When we have inversion, how do we fix it? Yeah. All right. Swap operation. We can swap these two elements, right? After the swap operation, this inversion is gone. How about that? This inversion is gone after the swap operation. Then we try to find another inversion. If we get another inversion, then we apply another swap operation. Then that inversion is gone again. Sooner or later, all the inversions will be gone, so the whole array is sorted. How about that view? So that is a completely different view from our previous selection-based view. So we get a new solution. All right, here, so let me, based on that view, let me summarize the implementation idea here. Yeah. The basic idea, we want to remove all the local inversions by local swaps. Yeah. All right, here, the procedure. Yeah. Step-by-step procedure. First, start from the first element for each scan. Yeah. Each scan, yeah, we start from the first element. Yeah. All right. Do swaps one by one from left to right if necessary. Yeah, here I put if necessary because when you scan from left to right, you examine two adjacent elements. Yeah. Here I didn't mention, but you need to examine two adjacent elements. How about that? Two adjacent elements. When you detect there is an inversion, you do a swap. So that's why I say if necessary, because you may not have an inversion, right? You may not get inversion, then do not do anything. Just move to the next two adjacent elements. Next pair of two adjacent elements. Yeah. That's step 2. Step 3, start at the first in-place element. Yeah. You need to stop somewhere. Yeah. Although you may stop at the end, but you do not have to stop at the end. So why? So look at this procedure. The first time you scan the array, the first time after you scan from left to right, what is the result? The result is you put the largest element at the end, right? Because when you do local swap, local necessary swap, at the end, you will place the largest element at the end. That element is already in place. So in the next round swapping scan, you do not need to touch the last element that is already in place, right? So you start before the last element, but you get another element in place, right? So the second to last element in place, the second round scan, and so on. So every time when you do scan, you put one element in place. Yeah. So the step 3 start at the first in place element. Yeah, because you have a block of elements, block of in place elements, right? Yeah. So you build up at the end of the array, you build up a block of in place elements. So you start at the first in place element in that block, So that is the meaning of step 3. Okay, yeah. So based on this procedure description, now we can apply our sorting algorithm, right? Yeah, we can apply it. Yeah. All right. Okay, yeah. So this property we derived. So there is one element in place for every scan, right? So the in place element of each scan appears at the end of the current array. Yeah. Appear at the end of current array. The current array becomes smaller and smaller, right? Yeah. Current array. So we have a current array. Yeah. All right. The current array is a subarray that excludes all the in-place elements. Yeah. All right. So that is these 3 properties we derived from our working procedure. Yeah. All right. Then at the end, we summarize. Yeah. So this method, we have visual imagination. The swap looks like a bubble moving from left to right, right? Moving from left to the right. So we call it bubble sort. We learned this before. Yeah. In CS 2250, we already learned the bubble sort. But here, we use that solution because that solution is pretty special. We use it to explain our new view, new idea, new thinking for the problem solving, in our problem solving. Yeah. All right. Yeah. All right. So at the end, when we look at efficiency analysis, it is similar to that of the selection sort. Yeah. Pretty similar. Yeah. And when we look at the basic operation, because in efficiency analysis, we need to look at the basic operation. Here, I just ask you one question. What is the basic operation in this problem? Comparison or swap? Because we need to do comparison. We also need to do swap, right? But which one is based on our definition of the basic operation? It happens most frequently. This type of operation dominates the whole algorithm. Which one? The answer is comparison. When you examine 2 adjacent elements, you always need to apply comparison. But for swap, you only need to do necessary swap, right? If there is no inversion, you do not do swap. Only when there is an inversion, then you do swap. Yeah. So for that reason, comparison is the basic operation. All right, so let me finish video D.2 right here.